Today, what I want to talk about is the situation of dealing with severe overlap where you just can't use COSY to trace your way through a spin system. So I was hoping we would have had the a TOCSY problem last week but you have it this week. So you're going to start your homework with this TOCSY-oriented problem where you're going to very nicely use TOCSY to pick out spin systems where you've got at least one resonance in the spin system that's distinct, and you can sort of pick out the other resonances even if there's a little bit of overlap. But what we're going to be dealing with today is using HMQC or TOCSY or HSQC TOCSY to get the carbon dimension in on the action so that we can deal with severe overlap. And sort of to review, if we think of, say, the COSY technique, where we usually are able to walk our way through spin systems, we might walk from one CH to the next and to the next. And by comparison, so this is COSY. By comparison, in TOCSY, we get the advantage that in addition to getting cross peaks for the protons that are directly coupled that you get COSY together, we can hop from proton to proton by spin-spin coupling. So we still are walking through the spin system and we can get cross peaks, which means if this proton was in a little bit of a muddle, if this proton was overlapping with a bunch of other stuff, you could still correlate the proton attached to this carbon with the proton attached to that carbon. But you're still having to deal with having something that's exposed. So what HMQC TOCSY, and these are just slight variations in pulse sequence. It's not that different in terms of what they do from a practical point of view. The example that I'll be using in today's class is HMQC TOCSY. I think the homework may be HSQC TOCSY. Anyway, what we're going to do with these two complementary techniques is get the dispersion. So it's sort of like TOCSY, but with the dispersion of the carbon dimension. And so what this is good for specifically is it's good for overlap. And you're going to have two examples. So we implemented this in the course in 2011. I had started teaching about it, I think, in 2004, and it really was a wonderful TA, like James, somebody who really brings tremendous ideas to the course, who finally got this up and running on the spectrometers. And so we're going to have two problems this week where you get to take advantage of this, and that will be the fourth and fifth homework problem, where there's some moderate to severe overlap, and it's going to really help you pick out the spin systems. So it's good for overlap. And what's nice is if you vary what's called the mixing time, which is a parameter basically that deals with how much transfer you can get. It takes transfer, these types of coupling occur on the time scale that's sort of 1 over the J value. In other words, it occurs on the time scale of tens of milliseconds. And so if we vary the time scale of mixing from a few milliseconds to tens of milliseconds, we can sort of walk through the spin system. say by varying the mixing time. So it can be used like COSY by varying the mixing time from short to long. So I think where I want to start us, because this sounds very abstract, where I want to start us is a diagram, and then we'll actually move on to a concrete example, which I've taken from this book I mentioned that I used for the 2004 when I introduced this Croasman and Carlson. So let me share my screen, and I'm going to bring us actually to the third page of our handout. So this is the third page of the handout. So I wanted to start maybe with TOCSY, which you should be familiar with because we talked about it a few lectures ago when we looked at the grammacidin S. So TOCSY is very much like COSY, and this is just my little pigeon drawing here where I've sort of cartooned isopropanol. And so, or propanol rather. And so this is my little cartoon drawing of the spectrum of propanol. So if we label our proton resonances A, B, C, and D, the OH is proton B. It's a singlet. It's not coupled. It's part of a separate spin system. Hydrogen A is the one, the triplet that's alpha to the CH2 that's next to the oxygen. Hydrogen C is the sextet, the methylene group, that's beta to the oxygen. And finally, hydrogen's D or the methyl group. And so remember, in a TOCSY spectrum, we have our diagonal here, and then we have our cross peaks. So A crosses with C, and that's a COSY-like cross peak. And AC crosses with D, and that's a COSY-like cross peak, just a 3-bond coupling. But then we also have this cross peak associated with TOCSY, which A is crossing with D. And so that's this cross peak. So basically all the protons in the spin system, remember a spin system is a set of J-coupled nuclei. Now on our F1 dimension, we also have proton, right? So we've got our proton spectrum A, B, C, D right over here. Now the next technique that we introduced earlier was the HMQC, which correlates your carbons with your protons. So here again is our proton spectrum, A, B, C, D. Here are our carbon resonances. This tells us that carbon 1 is correlated with A, carbon 2 is correlated with B, and carbon 3 is correlated with C. So we always mark our little numbers down to help us keep track of who's who.
James,
now,
2C and 3D.
What?
Isn't it 2C and 3D?
Did I? Oh, yes. Thank you. Thank you very much. Let me fix that. So 2C and 3D. Thank you very much. All right. So in HMQC TOCSY, we get sort of both of these features within a spin system now. Here are our carbons, and here are our protons. So in the F1 dimension, we have carbon. In the F2 dimension, we have proton. And what's interesting about this then is you can look and say, okay, if we're going in this direction, if we're going along the F2 dimension, you can say, sure, A is correlated or is connected with C, and A is also connected with D. And you'd say, okay, what's the big deal of this? But the really big deal is that we can also go along the carbon track. So we can also say that 1A is correlated with that the protons on 1 connect to the protons on 2 and to the protons on 3. And if we vary the mixing time, we can do this sort of stepwise. So that's with a longer mixing time, because we wouldn't know, okay, is 1 connected directly to 3? But you can do that over here with a short mixing time. And the first cross peak that comes up is 1 to 2. And then here we've got 2 to 3. And if we continue now, this peak will come in here with a longer mixing time. And that's going to be what really helps us out. And I'll show us that in a real example, which I took from this Croasman book in just a second. Any questions at this point? Because I know this introduction has been a little bit on the abstract side.
So no matter how long you do the mixing time, you're still only going to get cross peaks within the spin system. Is that right?
That's exactly right. That's exactly right. We're only going to get cross peaks within the spin system. And that's what makes this particularly powerful. We only get cross peaks within the spin system.
So is that, I was trying to think like, well, how is this different than HMBC?
Ah, very good question. So I'm having give me one moment here. I'm having a little bit of trouble. I can't seem to escape from the screen sharing. All right, I'm gonna try. I may have to reboot our Zoom session here because it's not letting me stop the share. Woo, this is weird. Give me one moment and we're going to get back to that question because it's a very important question that you're asking. Huh. All right, I'm trying not to have to quit, but I may end up having to quit Zoom here in order to bring you back. Can you see my whiteboard now? What do you see right now? Do you get my whiteboard? No.
Not on the shared screen. We could probably pin that video so we see the whiteboard.
Yeah, for some reason it is stuck. All right, what I'm gonna do is I'm going to quit Zoom and what's that?
If we pin your video, we could see you on the screen. So you might not have to do that.
I think I'm still gonna quit Zoom and because it seems to be partially crashed. So I'm gonna quit Zoom and restart it. So come on back in. So I'm gonna quit assuming I can, and then come on back in. So the question that was asked very, very aptly was, what's the difference between HMBC and HSQ TOCSY? And I think this actually is going to set the stage very nicely. So let me show you first a molecule, and then, because this will be the basis for the current example, and I'll use that to illustrate the point. So here's the molecule that's going to be our reactant in the problem that we're about to see. So the molecule that's going to be our reactant is called Bromomalliol. It's a natural product, probably a marine natural product because it contains a halogen in it. So we have a cyclopropane ring. Let me redraw that bond of the cyclopropane ring. It's on the lower face. Okay, so this is called bromomalliol. And I'll use this to illustrate the example of the difference. So in TOCSY or in HSQC TOCSY, we can walk our way through this spin system. In other words, we need this hydrogen to trace to these two hydrogens to trace to these hydrogens, even though we're going to be going through the carbon-13 dimension. In the case of HMBC, you don't need any hydrogens. So sure, we'll get an HMBC cross peak between these CHs and this carbon, or at least we will most likely, but we have to have hydrogens for an HSQC TOCSY. In HMBC, this methyl group that's isolated won't give any cross peaks with HSQC TOCSY, but it will give a cross peak with this carbon, and this carbon, and this carbon. So it's different because this is going, the HMBC is going through the carbon-hydrogen couplings. The HSQC TOCSY is only going through the hydrogen-hydrogen coupling. So that's the key difference. And what that means is that this technique shines for elucidating spin systems when you have severe overlap. And that's what today's example is going to be about. So this molecule, this compound, was left in an NMR tube in the fridge for 18 months in deuterochloroform. And what happens is chloroform oxidizes to give acid, to give catalytic amounts of H+, or more specifically D+, but it's a catalytic amount. So basically you get a chain reaction, a catalytic reaction that's driven by H+. And this molecule underwent isomerization to an isomer with 5 CH2 groups. And you notice that the reactant, the original molecule, only had 4 CH2 groups. So its structure has changed a lot. It has an oxygen, but no alcohol. And so the researchers ended up wondering what they had. And the problem we're going to see is that the spectra overlap severely. So I want us to take a look, and we'll start with the spectrum of this. Hopefully I can do this time with the handout without things going kablooey in Zoom. So I'm going to share the screen and we're going to start with our first page of the handout. All right, so this is the HMQC spectrum of the molecule, and I want to show you what a mess the proton spectrum is on the F1 dimension. So we've numbered our carbon resonances here, and carbon number 1 and carbon number 2 are quarks. Carbon number 1 and carbon 2 are, well, we'll see them in a moment, but they're at 80 or 90. So I'll just jot this down over here. C1, C2, they're about 80 parts per million. So they're way downfield. And we're going to see that that's, since they're quarks, since we have no alcohol, since the molecule has an oxygen, those are carbons that are part connected to the oxygen. So, right, it's going to be C1O, C2 in some way of connection. But let's look at our HSQC, our HMQC, and we can see just what a bloody mess this is. I'm not even going to try to label these peaks A, B, C, D, because this area is just too much of a mess for me to make my way through. But when I look at the correlations, this peak comes up as that's correlating with this, that's correlating with number 4. Number 3, so 3 is a methine, 2 is over here. Those are about the only resonances that don't end up, maybe the next one up here, that don't have some terrible overlap. So number 5 ends up over here, but we see there's another one over there. That's number 8 that's over there. This is kind of okay. These guys are correlating to 10. If we continue under this mess here, we can see, okay, we've got 14 over here. And we've got, it looks like 12 is right in the middle. I'm going to zoom in just a little bit to facilitate my writing. And we're going to see in a moment, we just can't make our way through the COSY. Under this mess here, we have 8 and 7 are giving cross peaks here. Over here, it's actually not too bad. We've got 4 singlets for methyls. We've got 9, we've got 11 correlating over there. Here we've got 15 and 13 giving rise. There are 2 singlets that are very close to each other. Here and here we've got number 7 is under number 8, and number 7 shows up here. So this thing is just a really crowded proton spectrum. If we go to COSY and we try to take our spin systems and work out our spin systems, because normally I say, okay, you go ahead next to the COSY and you try to walk your way through the spin systems, and then you try to use HMBC to put the pieces together. But we go to the COSY spectrum here on the next page, and it's just a mess, right? I mean, this was 4, this was 10, this was 10, this was 8 and 5 lumped on top of each other, 14 and 12 and 14. And then over here, we had 8 and 7 lumped on top of each other, and 3. And then we had 9 and 11 as the singlets, which we don't need to worry about yet. And we have 12, and we have 15 and 13 over here as the singlets. And then we have 7. And we try to make our way through this COSY, and we can start to see a cross peak here. So we can at least say, okay, 4, which is a methine, is crossing with 10, right? So at least we can make some sort of correlation here. Then if we come over here and we say, who does 10 cross with? 10's diastereotopic. They cross over here, but I'm, I'm not really sure because we've got stuff lumped together. So 8 and 5 are lumped together over here. So this is 10 with 8 or 5 or both. Over here, we've got 10 with 8 or 7. Or both. So I really end up lost. Then maybe I could try to come in on number 3 and say, well, 3 is crossing with 8 or 5. But there's so much uncertainty here that the only thing I've really gotten out of here with any confidence is if I go back to my structure and I try to build up. Try to build this thing up. The only thing I've really been able to take away is, yeah, C4H is crossing with C10H2. I think maybe it's 8, but it could be 5 or it could be 7 that I'm crossing with. So I'm in a little bit of a pickle over there, and I haven't done very well. So I want at this point for us to take a look at the HMQC TOCSY. So I'm going to go back to the handout. And unfortunately, the way this is plotted, they haven't given us all the plots with various mixing times. All right, so, and I think I'll come right over here. So I think that's page, what are we on? I think it's 5 of your handout. So they give us a plot with a 14 millisecond mixing time. And we can start to see what's going on now a little bit better over here. Because if we look at this with the 14 millisecond mixing time, you can say, okay, if we just move along the H1 dimension, right, this is this whole mess that we had before, right? This is 4, and this is 10, and this is 10, and we continue. You could say, okay, we walked from 4 to 10, and you'd say, all right, what's the big deal? We're still going to end up in this muddle of protons over here if we continue to walk. But we get something else new when we start to walk along this dimension. When we start to walk along this dimension, when we walk along the F1 dimension, now we get completely unambiguous types of directions. So we go from 4 to 10 here, but then look over here when again we move on the F1 dimension. Now we unambiguously move from 10 to 8. So in other words, we've now set up that we have our C4H connected to the C10H2 connected to C8H2. And that starts to be really, really nice. And then over here, you look, this is right, this is number 3 over here. And now we're going from 3 to 5. There's another one coming up that I'll show you in just a moment. But here you can see this well-developed cross peak is taking us from 3 to 5. So we're starting to actually build up just by moving up and down the F1 dimension. So let me put in this new information that we've been able to get out of here. So in other words, now unambiguously, we've gone from C10H2 to C8H2. We had C3H, we've gone to C5H. H over here. So we're starting to build up the structure rather nicely. Now, I want to continue by varying the mixing time because that's where we're really going to have the ability to just walk through. And I want to show you what they've done over here for us. So I'm going to go back to our handout. So what Croasman did in this handout is he did an expansion. They did an expansion of this region and they varied the mixing time. We would give you, and indeed in the homework, in problems 4 and 5 on the homework, we give you a series of mixing times where you get the whole spectra. But they just looked over here. So this spectrum here was collected with a 14 millisecond mixing time. So they go through, they run a 6 millisecond, 14 millisecond, 24, 36, and 83 millisecond mixing time. Now with 83 milliseconds of mixing time, you get the entire spin system is lighting up here. So the entire spin system ends up lighting up here where you have C14, you have C12, you have C7, you have C5, and you have C3. So coming back to the question of how this differs from an HMBC, these are all carbons that have protons that are J-coupled to each other. This is an entire spin system that's going to come up. So we already elucidated one spin system, the C4 to C10 to C8. And we started on this next one with C3 and C5. Watch how we can walk through the spin system as we vary the mixing time. So with 6 milliseconds, we've gone from C3H to C5H, and we can just see C12H2 beginning to come up. As we continue up to the 14, now we're starting to see this C12H2 coming up. So we're coming from C5H to C12H2. We continue to 24. That cross peak is well developed. We go to 36 and we go from C12H2. Now C14H2 starts to come up. As we continue to 48 milliseconds, now we go from C14H2 and we see that C7H2 has started to come up. In other words, we've managed to start at one end of the spin system and walk our way sequentially through the entire spin system. We've got the entire spin system now waiting for us, ready for us to pick this out. And so I'm going to draw this entire spin system on my whiteboard here. So we go from C3H to C5H to C12H2 to C14H2 to C7H2. We've blocked out our entire spin system. Now at this point,
sorry to interrupt. How do we know that 12 is coming off of 5 and not 3? I must have missed that.
12 is coming off of 5 and not 3. No, it's a very good question. There was indeed a little bit of ambiguity there because even at 6 milliseconds, we saw 12 starting to come up. So you're absolutely right. It could conceivably have done that, but you notice this one came up second, and there'd be no way at that point if we used our valence here, so imagine we had done that, there'd be no way to then connect C5 to C12. So basically, because the first thing that came up was C5, it was pretty clear to me. Now, I agree, if we had gone and we had started with, let's say, C5, if we had started with C5 on that track, we would have seen these two, both 3 and 12, come up at the same time. But here we saw 5 come up first. So we basically were able to sort of walk our way from here to here to here to here.
Okay.
Through the system.
Okay. Thank you.
So that's really what we relied on to build up the spin system. But I agree, had we started in the middle, it would have been more confusing. Other questions at this point? All right, now if we're keeping score, at this point we have the oxygen, the bromine, carbon 1 and carbon 2, and these are in the high 70s. These are both about 80 ppm. And we'll see that in just a second. They were cut off the expansion because they're quarks. These are going to be carbons that are connected to oxygen. We have C6, which is another quat, and then we have our isolated methyls, C9H3, C11H3, C13H3, C15H3. And so the next thing we're going to do is, now that we built up our spin systems, we're going to use our HMBC to put the pieces together. And you know that the first thing I like to go for is the isolated methyls, because those isolated methyls end up being linchpins where they have to be connected to a carbon or a heteroatom, but we know the methyls aren't connected to the oxygen. So they have to be connected to our quat carbons because they have no J coupling. They're all singlets. So they have to be connected to these C1, C2, and C6 carbons. So I'm going to give us an expansion of the HMBC at this point. And that should be the final page of your handout. So here's our expansion of the HMBC. So they've given us some tracks here. They've given us C3H, which we can use, but I'm going to start off of the isolated methyls, and I'm going to start with the low-hanging fruit. So here's C9H3, here's C11H3, and then it gets a little more complicated because this is C13H3 and this is C15H3, and they're very, very close to each other. So let's start with the easy stuff where I clearly can see them distinctly. So C11H3 crosses with C13H3. And C11H3 crosses with C5H. And C11H3 crosses with C1. And that's useful because at that point we've got some nice information. So let me put that on our whiteboard here. So C5 is crossing with C11, and we know that they're not directly connected to each other because they're not J coupled. And we also know that we're connected to C1 because C1 is a quat carbon. So here's C11H3, here's C1. C1 is way downfield. It's down at 81, 82 parts per million. So that's connected to an oxygen. And C11 is crossing also with C13. So we're using the HMBC to sort of give us a linchpin here to put together this piece of the molecule. This is what we like to do with HMBC. So let's continue over here. And I'm going to share my screen again. We'll consider another HMBC track. Now remember, HMBC is picking up 2 and 3 bond CH coupling. So let's go for another piece of low-hanging fruit. We'll go for the track associated with the C9H3. So C9H3 is crossing with C8H2. And C9H3 is crossing with C3H. And C9H3 is crossing with C2. And so we get those 3 cross peaks off of that. So let's go ahead and put that in. Now C2 was at about 77 or 78 parts per million. So it's also connected to an oxygen. Here's our C9H3. C2, it's also crossing with C3H, and it's crossing with C8H2. So those were our 3 cross peaks that we picked up off of C9H. So if we're keeping track of our scorecard at this point, we've used up C1, we've used up C2, we've used up our oxygen, we've used up our C9, we've used up our C13, and we've used up our C11. So all that's left for us is the bromine. And carbon 4 is pretty downfield, so it's probably going to be on there. And that methyl 15 and C6. All right, so let's return to our HMBC. Now, our 2 methyls are really, really close together. Our C13 and C15 is very, very close together. But we've taken all of our cross peaks off. We already know all of our cross peaks for C13 are going to be accounted for because we know we've placed C13 because it crossed with C11. And here's the complementary cross peak where C13 is crossing with C11H3. And every other cross peak we can already sort of account for. So this is C13. I'm going to just zoom in here. This is C13H3 with C5H. And this is C13H3 with C1. Right, because we have the same peak over here, and we have the same peak over here, we basically can account for those. Now, every other peak that we need to account for, we can now account for off of C15. So, for example, here, we can see that C15H3 is crossing with either C7H2 or C6. And it's actually going to be crossing with both because we know it's isolated. We know it's got to be on a quat to be isolated. I'll show you that in a moment. If we continue, we can see over here C15H3 is crossing with C4. And here C15H3 is crossing with C3H. So let's look at all of these cross peaks as we finish putting our molecule together, and then we're going to talk about the rearrangement very briefly. All right, so I'm going to draw C15H3 over here, and we know it's got to be on a quat, and in fact, we see what looked like a cross peak to C6. C6 has 3 valences on it. We weren't quite sure whether it was crossing with C6 or C7, but when we look at all of our valencies here, we see we had a cross peak with, let me just take my notes for all the cross peaks. We had a cross peak with C4. Since the methyl group can't be directly on C4, the methyl group is connected to it through C6. We see a cross peak with C3. Again, since it's not directly connected with it, it's got to be connected through C6. We see that somewhat ambiguous cross peak with C7, but again, we have no other place to go. That completes our skeleton. We have 1 valence left over here. That's where our bromine goes. That's the structure of the molecule. That's all the connectivity. I'm going to redraw this molecule now. We don't have the stereochemistry, but I'm going to give us the stereochemistry and explain the transformation that we observed. All right, so the molecule, the reactant molecule was a transdecalan. Like so. And this molecule was treated with acid, adventitiously or inadvertently treated with acid. And now here's our molecule redrawn. And I'm going to put in the numbering scheme from what we just have here. So this is our carbon number 4. This is our carbon number 10. This is our carbon number 8. That's our carbon number 2. Carbon 2 is connected to methyl group 9, C9H3. Carbon 2 is connected to the oxygen atom. The oxygen atom is connected to carbon number 1. Carbon number 1 is connected to C11H3 and C13H3. We happen to have an endostereochemistry over here. Again, you wouldn't necessarily know that. We continued our assignments. Here's carbon number 3, carbon number 6, 7, 14, 12, and 5. So the skeleton has stayed the same. What's happened is we've ring protonated right over here, generated a carbocation here, our oxygen has attacked, and so now we have this tetrahydrofuran ring. And the whole connectivity came out of basically using that combination of the HSQC TOCSY or HMQC TOCSY, and then the HMBC to stitch the pieces together. So this is a very powerful technique for dealing with severe overlap when a COSY or a TOCSY just isn't good enough and your protons are lumped on top of each other.